was reading an article recently about the X-29, which was a experimental jet from the early 80s, and like it sounded like about 80 to 90% of that was jury rigged. So they didn't say anything about using 7.2 volt drill motors, but that wouldn't surprise me either. But it was all airframe and engine and cockpit stuff was taken from old projects. So the idea of using current stuff off the shelf for development projects is pretty common, I guess, even at the highest levels of development. Okay, when I was a student, and I won't say when that was, but it was somewhere after Dr. Pansino and somewhere before now. Back in those days, the most popular video game was Pac-Man, and I saw some of my fellow students playing Pac-Man, and I thought, what the dumbest thing in the world, wasting your time on that. I just couldn't get into it. Well, a couple miles down the street, there was this bar we liked to go to. That was before I became antisocial. They had a game there called Frogger, and I could get into Frogger. For some reason, I liked that. It was this dumb little game. You had a frog on one end of the street. You had to jump over rocks, avoid the crocodiles and stuff like that, get your frog to the other end of the stream. And I really enjoyed that game. I see the kind of games they're playing now. The graphics and the video are just so much more realistic. And I'm saying, when are we going to really take the next step from just realistic to actually like 3D realistic? And I don't know that our next project is quite there yet, but they do have a 3D display. So I'd like to introduce the LED3 group, which is our next presentation.
For the LED Cube group. My name is Shayne Brown. I'm a electrical engineer in digital option. My expertise would be in the design and programming, mainly MATLAB and C++.
I'm Justin Moff. I'm also a digital option, and I have experience in the VHDL and coding aspect, as well as the circuit design and the actual construction.
I'm Jacob Stracola, and I'm also a digital option, and we've done a lot of projects in VHDL, so I consider that my area of expertise.
Our opportunity, there's a lot of video entertainment systems out there already. We wanted to do something that's different, that's unique, and also something that's a little more functional. So we set out doing that to make it something more efficient and useful. Then, as we got through the design process, we also saw that it had applications towards education, teaching coding, VHDL. Because when we went through it, everything was more, you programmed it, the screen spit out a number, and said it worked. There was no visual way to see that what we were doing, like what it did. So we saw that this had that potential to show what VHDL program's actually doing. Then actually, this past weekend at STEM Showcase, Dean Suris mentioned that this could be used in crystallization displays in the chemistry department. So there's another application for education that it can be used towards. So our opportunity was for the entertainment industry, like I said, more functional, a more efficient alternative to what's already out there, to get them something different and unique. And then education, so assisting the teaching of logic, VHDL programming, FPGA boards, which is how we're controlling our system. And then, like I said, also could be used in other aspects like chemistry to show different crystallization patterns and things like that. Our initial concept was to use a 512 RGB LEDs, because our cube is a 8x8x8 cube, so it consists of 512 LEDs. The initial design was to use RGBs to give us a broader range of color. The ones we actually selected would have given us 8 different colors. We were going to control that using an Arduino. One single Arduino was not enough to control everything we needed, so we had to use 2 of them together in a slave master type setup. And then also a self-made printed circuit board that would allow us to control all the lights more individually instead of as a group. One of the other things we were tossing around at the same time was using a Texas Instruments type of control board. Works very similar to the Arduino, although this one would have let us able to control it with just one board. So our strategy going in, biggest thing for us was our circuit design. So that was going to be where a lot of the uniqueness of this was going to come from. So we spent a lot of time with our circuit design, deciding how we wanted to do things, the parts that we needed to do that, and making sure that it was going to work the way we wanted to do that. So we spent a lot of time working with the circuitry. I think we actually started sometime last semester trying to figure out how we wanted to do it, make it work. Also with the pseudocode, which for anyone who programs, it's a good way to work through your code before actually making it. That way you can see what you want to do, figure out how you want to do it before you actually write the program. Makes it a lot easier. That way it flows better and it's easier to troubleshoot. Next phase was to actually implement our design. This is where we actually physically got all our parts in. We incorporated them to each other, tested different ones to make sure that they work well together. And the biggest part of this was our soldering. Justin talked more about that, but that was our biggest time consumer with this project. So we had to solder all 512 LEDs together, which is not very fun. It took a long time. Then also had to solder any of our control wires to our circuit. And also our printed circuit board, we had to solder all our chips to that. Next thing was our coding, which we did throughout the semester. A little more heavy in the past couple weeks once we actually had something to physically test it on. And then testing, which pretty much took us up right to the end. So this is probably the biggest thing. We did it throughout the whole process, but very heavy towards the end of the semester here. So our goals for this thing, for the project, were to be easy to program, which means it's modular and simple. Modular just means that we can interchange the programs with others and not have to rewrite everything over and over. So we want to make it modular and simple, that way we can move it around and use it over and over. We also wanted to have low production costs, that way it could be manufactured cheaply, so it could be a little more easily accessible. And the way to do that was to have less hardware, which is where our printed circuit board came in. Our timeline, starting off this semester, we were pretty on track for everything. We were hitting our deadlines, getting everything done on time. Our circuit design took a little bit longer once we got our chips in. I'll explain that here in a second why. But our biggest issue was with our construction. We had issues getting parts in, so they still actually haven't arrived. So we had to change our design slightly to adapt to that little challenge. So we actually weren't able to construct our product early on, so it changed our entire flow of the process. And then, as you can see, the coding took a lot longer than we intended because we switched we were going to be using an Arduino, using that type of programming to VHDL, so we had to change a few things up and then troubleshooting. Our budget, what I did here is with 2 columns. The left column over here, the 191, that's how much we actually spend on the project. It's all our parts coming in, and we were under our budget. The one on the right, the 143, was the cost of what's actually in the product. That's exactly the 512 lights, the exact amount of gates that we use, and all the minor components. So that's what it physically would cost for that particular thing to be built. Because for the LEDs, we use 512, but we couldn't order just 512 because we went through about 18 right off the bat that didn't work. So we needed those extras. So we spent the money on that, but the cost of the product, we didn't actually include that in because mass produced wouldn't cost as much as the 191. Biggest thing with any type of product is the customers. They're the ones who are going to be buying the product, and this is why you're making it. So our customers were educators, business owners, like entertainment industry, DJs, things like that. And then even general population, once it's out there, people might want something for this at home parties, things like that. We did a survey early on in the semester to see what customers actually would want. So we asked them what kind of programs they wanted to see, what they would look for in something like this. And the biggest response we got back were text and 3D designs. We initially were thinking about putting some games in the program, in the cube. Not many people wanted it. I think it was less than 10 out of the 50 or 60 that we had responses that we got back. We also wanted this to be affordable, so we wanted to keep the cost down. And easy to use. No, we didn't want everyone that wanted to use this to have a programming background, so we wanted to have the programs in there, someone can walk up, hit a button, hit a switch, and it would do what they wanted it to. Okay, some of our early on issues, like I said before, parts not arriving. We ordered 600 RGB LEDs, and they never showed up. They're still somewhere, we're not sure where. Also, incorrect parts. For our grounding, we were going to use MOSFETs, N-channel MOSFETs. We got sent P-channel MOSFETs, so they wouldn't properly do what we wanted them to. And then our biggest issue was the microchips are hard to solder. As you can see, there's a quarter. Those are our microchips right there, and I think they have, what, seven leads on each side. They were extremely difficult to solder, so that became an issue. Justin's going to elaborate more on how we fixed that.
So after we worked out all of our issues and our kinks and everything, basically, like you said, we ordered the RGB lights, which would have been a lot better for the cube. We would have had all the extra colors. We would have had that much more versatility and functionality with the cube. But they never came in. You'll probably hear about them in July or so when they show up. So the only downside to the RGBs is they're more expensive. And we could have ordered some more, but from where we were, they're about $1 a piece, and we weren't about to spend $500 to buy some RGB LEDs. So we decided just to go the single color. We went with blue, and that kind of solved that issue. So then, as far as the board, we went with the D0 Nano. We went with that over the Arduino, mostly because we have more experience in VHDL. And as far as the education aspect goes, it would expose students to more of what they actually go through in the program you're required to do. The D0 Nano also has switches and buttons actually on the board that we can use to switch to different functions, or reset it, or even shut it off if we want to. And then the 2-input AND gates, there's actually 16 of them that we used in this design on each board. And what those allowed us to do is it optimized our inputs and outputs. So instead of needing 72 inputs to control all 72 outputs, instead we only needed 24 inputs to control the same amount of outputs. And some environmental considerations we took into account were we decided to use LED3 solder. If it's going to be in an educational setting, then it could come into contact with children, students, or even the instructors that are using it. And we wanted to basically foresee different hazards like lead poisoning or similar issues. So the LEDs, like I said, we went with blue ones, and when we first got them, they weren't diffused. And this ended up causing a problem because, as you can see in the picture, they put sort of emit a beam of light. And when we put them in our cube array, as the light on the bottom is lit up, it sends that beam up through all the other lights. So it appears that the whole column's on, when really it's just the one light on. So we went through and we diffused each LED, which we did that by using a sanding block and sanding around the LED to give it that diffused look, which we felt made it look better. It has more of a glowing look to it, and you can tell that just one is on and not the whole entire row. So here is a 3D rendering of how we kind of planned the design to look. We shaded the LEDs in black just so they're easier to look in this picture. And essentially, we wanted to break our controls up so we can just use a coordinate system with X, Y, and Z. So we would just send in, we want this X and Y coordinate, and then the Z's are actually the levels going up the cube. And the lights they're actually held up with the columns going up and down are the positive leads, and they're all soldered together the whole way up the cube. And they're done in sheets. And then the grounds are actually common for each Z-axis level, and that helps, since they're all common, they kind of hold the cube together in a cube shape. So here it is after construction. After we got all our soldering done and our base and everything all put together, that's the final product that we ended up with. The way that we put it together is first we made the sheets of LEDs, which we used that white base that you see there as kind of a jig to make sure that each sheet was actually square. And using that jig, it really helped. The hardest part of putting it together is probably making sure that it was a cube. We didn't want it to be like off and look all like messed up. So the jig really helped with that, and I really don't think it would have been possible otherwise. And it was a lot of soldering. Basically every single end of each LED, both leads on them, they had to solder together to another LED. And then after that, we had to solder all the wires, so 64 wires on the bottom, from the cube to the small little PCB board that we made. And here's the cube after we got the code all put on it, and we started running some testing. We lit the whole cube up, and we do this by using persistence of vision. So right there, you see the whole cube lit, but really it's cycling through each individual layer to turn on the LED. And this is happening so quickly that the human eye can't actually pick up on it. But if it's not cycling through fast enough, you will notice a slight flicker, or almost looks like the LEDs are shaking. And you can kind of notice it. So we were aiming for about 60 frames a second for our LED, and this meant that since we're lighting up each layer individually, each layer could only be lit up for 2 milliseconds. And here's this is our original design for our circuit board. We went through, they're called Express PCB, and they give you their software that you go in and pick the dimensions of your board. They have different options price-wise. For us, since we were originally going to use RGB, we needed one board for each color. And so we got, I think, 3 boards. They're 2.5 by 4 inches, and it was like $70. But unfortunately, the RGBs never came in, so we're only using one. And so, as you can see in this picture, you have your 16 AND gates, which are each of those yellow gates you see on there, and the 40-pin connector. So basically our A's and B's, which is our X and Y coordinates, coming through from the D0 nano through that pin connector, and they go to the AND gates. We have all of our A input on our AND gates connected commonly through columns up and down. And then all the B's run the other way, and then the outputs are next to each chip. And we actually wired those straight up off the board. We thought that was a lot easier than trying to wire them all to the edge of the board or something, because as you can see, that's a whole lot of wires, a whole lot of leads. If any of them get crossed, it can basically mess up the circuit. And then in the bottom right there, you can see the 8, those are the 8 pads. That's what we use for the grounds, because we only need to pick which layer of grounds that we wanted on. It's for Z axis. And the extra pins down in the bottom left, that was just in case we needed something extra, if we were going to try and add something, or if one of our pads weren't working. They're kind of a good backup. And so here's the chip after we ordered it and they shipped it to us, and it looked really nice. Originally, it didn't have all the chips for the connector on it. We had to put those on, which was sort of a pain because since the chips were so small, we would try and solder it, and sometimes it would flop over and cover all of them, and we'd have to pull it all off and try it again. But getting them professionally made with the solder mask and everything, that kind of helped prevent that from happening. And yeah, so then after we, like I said, sometimes they flop over, and then we got to the troubleshooting. We actually found that we did have a few spots, since they're so small, that we thought they were soldered down, but just one pin on one of the chips, if it's not actually contacting the pad, it caused our outputs not to display correctly. But after some troubleshooting, we found out what pins weren't actually there. We got those all pulled around. And other than these few problems, the chip worked exactly how we designed it to. And so now I'm going to hand it off to Jake, who's going to go into more detail about the coding.
All right, so basically, once we have all the hardware done, we need to implement the software side of it. And so how we did that was with VHDL. And VHDL stands for Very High Speed Integrated Circuit Hardware Description Language. VHDL is obviously nicer. And so basically what it was in the 1980s, the Department of Defense, they were building circuit boards, electronic pieces for their hardware, and because transistors were going through such a quick phase of development, their programming couldn't keep up with it. So they said, all right, we have to design some sort of language that will keep up with it. So they came up with VHDL. So I know it's a little scary, but here's some code. And basically all it is we have a clock, and all we do is we just make variables that keep track of where we are in that clock. So basically we just keep track of like how many seconds we have, and then a display counter, and then also just a second counter to help with some of the coding. And so basically the display counter counts those Z planes so that we can cycle through and control it that way. And so this is just some code behind it. And then the code to actually display things is a case statement. So basically you just say, okay, here's my variable, take a look at this variable and do these things whenever it's this condition. And so for our first second, we have a display that displays YSU. And so for 1 second it displays Y, the second it displays S, and so then the third it displays U. And so for Y, those pins that were on the board, we just basically say, make it 1 to activate it or 0 not to activate it. And at this point, it just becomes really easy to code. You just go through and you just code what you want. And so it also just makes it really easy for just really anything that you want to do. And so when we actually sat down and tested it, we said, all right, well, our LEDs, those are pretty efficient. They don't use much power, but we still want to know how much it uses. And so when we kind of just sat down and just theoretically said, all right, how much power is it going to use? We kind of came out to about 9 watts, and that's what the board included because it runs off of USB power. So that's only, like 5 volts. And then for our actual, even with the power supply not plugged in, it will still run off of USB, so it only uses 2.5 watts. I mean, your average fluorescent bulb is 13, so I mean, you're not really using that much power. Some of our goals was just programming. We wanted to get our programming, set out, simple to use. We wanted it to, just be solid. And then for our unit cost, it comes out to be $143.55. So we were under budget for our $300, and then if this is mass produced, that will bring the price lower. So it's also a good pricing point for just people wanting to buy it. It's not too expensive, so that's what we're aiming for. And we'll show you a demo of our project.
right now it's just scrolling through YSU. Like you said, every second it changes. And then this is just a scrolling function we have where every second it will turn on a different plane. It's actually what we have displaying up right now. It's probably our brightest and easiest to see program. And then this program, what it's doing is it's filling the cube layer by layer from the bottom up to the top. Once it reaches the top, it drains from the bottom up to the top. And then this is just it's a cube, and there's three different sizes, and it scrolls through each one. And we just sped it up so it looks like it's pulsing.
So our next steps that we see this going, future studies. So we could either increase the size of it, we could just pretty much do anything with it. It's just that versatile. One of the other things too is a mobile app. So people, like using their smartphones, and so if they have some sort of program that they can use, say I want it to, save this, and so it will, program itself, and then it will say whatever it is that they want it to. The other thing was the RGB LEDs. That would give us, about 8 or 7 colors instead of just blue. So you could use, you can make it like mood lighting. I mean, you could just really do just everything with it. Gaming programs. So like some people wanted, some gaming programs. I mean, maybe 3D Pac-Man eventually. The possibilities are endless. It's just a matter of, how far you want to go with it. And then, larger cubes. Ours is 8 LEDs cubed, so you could go, 9, 10, 30, whatever you want. And then, basically what we learned, we have to be adaptable. I mean, we had parts that didn't come in. We're like, oh, soldering should be a breeze. It wasn't. So we just really needed to be able to change how we approach things. And then balancing customer wants and needs. We thought a lot of people would want games. And then we had that survey, and people said, no, we just kind of want it to be, kind of its own little entertainment center. And then, the design process. So it was difficult, but it started sorting itself out, and it was definitely a learning experience. And then special thanks to the people in the electrical engineering department, Dr. Jolie for heading this. Mr. Caven basically taking his free time out to try to help us with this. Mr. Zapka too, he helped us a lot with the VHDL. And then Jim Cook, he was really the brains behind the logistics of just really getting everything together and being able to help us do this. And then the department as a whole. So thank you for listening to our presentation. Are there any questions?